Hello, it's time for physics again. This is video lecture 19.1, our first lecture for chapter 19, which is entitled The Kinetic Theory of Gases. And if you are interested in further reading in chapter 19, this video lecture is about sections 1 and 2, which introduces Avogadro's number and what are called ideal gases. And in fact, ideal gases are mainly the interest of this whole chapter. But first, a word about what kinetic theory of gases means. Well, as you know, kinetic means motion. And if we have a gas in a container, like our apparatus we talked about in chapter 18, we know that the various atoms and or molecules of the gas are zipping around, moving around inside that container and fill the entire volume available to them. And they are bouncing occasionally off the walls of the container, and they are occasionally bouncing off each other. And we'd like to understand the properties of a gas in a container like that. And how are we going to do it? Well, there's probably going to be a lot of atoms or molecules. We're not going to be able to watch every single one move around or analyze the motion of every single atom or molecule. We wouldn't even want to do that. What we really want to know are what are the values of measurable things for a gas in a container, like its pressure and its volume and its temperature. Those are the three key things: pressure, volume, temperature. And it turns out that you can calculate those things, as well as measure them, but you can calculate them by looking at an average kind of behavior of all the atoms and molecules. And that's what this chapter is about. And you'll see how we do that in a future video lecture. But the point then is kinetic theory is about studying gases by averaging the motion of its constituent atoms and molecules. Just to be clear, obviously the common gases at room temperature and atmospheric pressure that we're used to having around us are the various gases that make up the air we breathe. That's mostly nitrogen and oxygen. But there's also some carbon dioxide, some water vapor, right? Those are all diatomic or polyatomic molecules, right? Nitrogen gas is N2, two nitrogen atoms bonded together to make an N2 molecule. Oxygen is also diatomic, two oxygen atoms bond to make an O2 molecule. H2O, of course, is three atoms bonded together, or CO2 is three atoms bonded together. Those are molecules with two or more atoms bonded together. Then there are the so-called inert gases. Oh, hydrogen, by the way, is also diatomic. Then there are the inert gases like helium and neon and argon and krypton and xenon. They're all monatomic, just atoms. So either way, whatever the gas is, you have either individual atoms zipping around inside a container or molecules zipping around inside a container. Of course, you have mixtures of gases as well. That's what we're studying in this chapter. And we're going to study all of those in a particular limit with a particular model called the ideal gas model. What is that about? In the ideal gas model, we're studying the pressure, volume, and temperature of any gas at what's said to be low densities. What do we mean by low density? Well, if we have a gas in a container, then of course we've got the atoms or molecules zipping around, filling the whole volume available to them. That's what a gas does. But you don't necessarily have to force yourself into a situation where there are a lot of atoms or molecules inside that container. And low density just means not a huge number of atoms or molecules. A low enough number that they only rarely bounce and interact with each other. That's what we mean by low density. Because it turns out something really amazing happens to a gas at low densities, or any of the gases at low densities. They all behave the same. It doesn't matter whether it's a container with helium gas, or nitrogen gas, or oxygen gas, or water vapor. They all follow the same equation that connects their pressure, volume, and temperature. And that's what these words universal behavior mean. Universal in the sense of the behavior is the same for any low density gas. It doesn't matter what the actual atoms or molecules are. That's very powerful. So the restrictions to the ideal gas model are this. They follow from the requirement of low density. The particles do not interact strongly with each other. If there's low density, there aren't that many of them in the container. They only rarely get close to each other. But if you pack a huge amount of gas into a container, then they're going to be bouncing off each other all the time. We don't want that. Next, the fraction of the container's volume taken up by the particles themselves is ignorable, right? Take all the atoms or all the molecules and take all their volume, and it is a tiny fraction of the volume of the container itself. Again, that follows from low density. If you have those conditions, then you can prove, or you can demonstrate, by experiment. This is an empirical model or law, studied by lots of people under lots of experimental conditions. But you can get a nice little model formula relating pressure, volume, and temperature of the gas. And I'm just going to state it. And if you study ideal gases in other classes, you might hear people's names attached to this. That's fine. But this is just an empirical model to study the behavior of any low-density gas. And it's this formula right here in the middle of this slide. The pressure times the volume, I'll write it like this. The pressure times the volume is proportional to the temperature. And then to make an equality, we introduce two things. Something that measures the amount of gas, and then just a constant. So let me say more about each one of these terms. First, the pressure term, the P on the left. Let me first emphasize it's the absolute pressure of the gas, the actual pressure from the force per unit area of the molecules bouncing off the walls. It's not what's called gauge pressure. And what is gauge pressure? Gauge pressure is basically an engineering term. Gauge pressure is the deviation of the pressure from atmospheric pressure. A lot of times engineers and experimental physicists, that's what they actually measure with a pressure gauge. Is how much the pressure of the gas deviates from atmospheric pressure. How much above atmospheric pressure is it? Or how much below atmospheric pressure is it? That's called gauge pressure. Gauge pressure, again, is the deviation of the pressure from atmospheric. It's called that because that's what most pressure gauges measure. We don't want that in the ideal gas model equation. We want the absolute pressure of the gas, the actual pressure from the molecules bouncing off the walls. That's important. The V there is the volume of the gas, which is the same as the volume of the container. That's what we really mean, the volume of the container that the gas is in. On the right, the first term is little n. That's the number of moles of gas you have. It's a measure of the amount of gas. We're going to talk about how to get that number. Then there's the T. That's the absolute temperature in kelvins. Must be in kelvins, not degrees Celsius. Can you think about why that can't be? Why can it not be that that temperature quantity on the right side of this model equation could not be in degrees Celsius? Well, for one simple reason, assuming you could cool the gas low enough without it liquefying, which you could do under certain conditions, you could end up being on the negative temperature side of the degree Celsius scale. But a gas will not have negative pressure on the other side of the equation. So the T there has got to be the absolute temperature in Kelvin. Remember, that's the SI unit of temperature anyways. Then the other symbol on the right is just a constant. Its symbol is R. Whoops, pardon me. Its symbol is capital R. It's called the universal gas constant, or I like to call it the gas constant per mole. But universal gas constant because it's the same value for any gas. And here's its value measured in SI units. 8.31, sometimes you'll see 8.314, joule per mole times Kelvin. You can convince yourself that those have to be the units of R in order for all the units in that ideal gas law formula to be consistent. All right, that's what we're going to use for this whole chapter. That's the ideal gas law model equation that relates pressure, volume, temperature, and some way to measure the amount of the gas, in this case, the number of moles. Now, depending upon how recently you've had general chemistry, high school and or college, you might be a little fuzzy about how to find the number of moles, little n. So I want to just describe for you two different ways to calculate the number of moles of a gas. It's just a way to measure how much gas there is. Two different ways. Number of moles of a gas. That's what the little n means, the number of moles. Well, it's really just counting. Here's one way. Take the total number of particles. I'm using the word particle to represent either atom or a molecule. Total number of particles, symbol, watch out, capital N, there's a lot of n's here, divided by Avogadro's number, symbol, capital N sub capital A, where I remind you that Avogadro's number is 6.02 times 10 to the 23 particles per mole. You can think of that as the unit of Avogadro's number, particles per mole. So if I want the number of moles, I just take the total number of particles divided by how many particles in each mole. Capital N over capital N sub A, the total number of particles over Avogadro's number. That's one way to get the number of moles. In order for that to work, you have to have the total number of particles. Here's another way to get the number of moles of the gas. It all depends on what you're given in the problem. Another way to get little n. Take the total mass of the gas. Could be in grams or kilograms. Those are the two most likely. Divided by what we're going to call the molar mass, which is the mass per mole. You might have heard that called atomic mass, atomic weight, and all kinds of terms. Okay? But you take the total mass, M total, let's say it might be, for example, in grams, in G, over the molar mass, the mass per mole, your book symbol there is just a big M, and that would be in grams per mole. Where do you get that thing called the molar mass? You get it from the periodic table of elements, because that's what's called the atomic mass or atomic weight. Well, it depends on what you were taught as its name. Right off the periodic table, because that's in grams per mole. Okay? So that's another way to get the number of moles. The total mass in grams over the molar mass in grams per mole. Okay, so really important formula up here. The ideal gas law equation. Pressure, volume, number of moles, gas constant per mole, absolute temperature. But I do want to show you another way the ideal gas law is written. And it's purely for convenience to have this second way. Let's make the following substitution. Let's write the number of moles as the total number of particles of the gas divided by Avogadro's number. So back up in the ideal gas law, just substitute for little n, big N over N sub A. And I did that here, and I did a little grouping, but there it is, big N over big N sub A. And I did the grouping that way because the gas constant per mole, R, and Avogadro's number, N sub A, are both basic constants. So we can just take those two divided by each other and define a new constant, symbol K sub B. Name Boltzmann's constant, after an Austrian physicist in the 1800s. And so, plugging in numbers, the gas constant per mole, 8.31 joule per mole Kelvin. Avogadro's number, 6.02 times 10 to the 23 particles per mole. Particle isn't a true unit. And you get 1.38 times 10 to the minus 23 joule per Kelvin. And so, if you do that, you can get a new version of the ideal gas law. pressure times volume, that's still the same, equals total number of particles, capital N, times Boltzmann's constant, K sub B, times the absolute temperature. So let me write them both forms of the ideal gas law side by side, or lined up. PV equals capital N kBT, or PV equals little n RT. They're equivalent, but just don't get confused over the symbols. Little n is the number of moles, big N is the total number of particles. Kb is Boltzmann's constant, for which we have a value, and big R is the gas constant per mole, for which we have a value. So we will use those both interchangeably throughout this chapter. And the one we use in any given situation is just based on what's most convenient. Okay, I want to show you now a couple of Wiley Plus videos, which are actual demonstrations of phenomena with gases in a container, and we'll model the gases in the container as ideal gases. In fact, they're both just going to be air from the room. So now let me change over here. All right, now in this first video, the person is going to take a helium-filled balloon, a balloon filled with helium gas. We're going to model the gas as an ideal gas, model the helium inside as an ideal gas. And he's just going to reduce the temperature of the gas and see what happens.
Liquid nitrogen, a helium balloon. You can see it's a helium balloon because I lift and it goes with it. I take my helium balloon, I place it in the liquid nitrogen, kind of turn it a bit just so it gets cold all over. Observe what's happening. Here we go. Down he comes. And up he goes.
Okay, so now let me get back here to where I can see here. All right. So what are we seeing here? Okay, so first of all, clearly the gas had some initial volume and it was at room temperature and at atmospheric pressure because it's surrounded by the atmosphere. And by the way, it stays surrounded by the atmosphere, so the pressure stays constant at atmospheric, even when he just sits it on top of the liquid nitrogen. So if we go to the ideal gas law for this experiment, we think about the conditions. What's constant in this experiment is the pressure. But we put it in contact with the very cold liquid nitrogen, so the temperature of the gas goes down. Sorry, you need to see what I'm writing, don't you? Right? The pressure is constant and the temperature goes down. Therefore, to satisfy the ideal gas law, the volume of the gas has to go down as well. But that's what you saw. You saw how the balloon kind of contracted in. Its volume got less. That's all he was trying to demonstrate. But it is showing the ideal gas. As the temperature went down and the pressure was constant, the volume went down. Then when he took the balloon away, the contracted balloon away from the cold and let it come back to room temperature, its volume expanded. It got bigger again. All right, just showing you how that is consistent with the ideal gas law. Here's another one to watch. Go back, make sure you can see it. All right, here we go.
A hot water bath. A bath of ice water, a bath of liquid nitrogen. What we have here is a constant volume sphere with the pressure gauge attached to the top. We're going to put this in each one of these baths, and we're going to watch what happens as our pressure gauge changes. By the way, it's reading about 730 millimeters of mercury right now in room temperature. Hot water first. We should observe the change in our pressure quite a bit. Now gone up quite a bit. Ice water, once again, a change in our pressure. It's going down quite a bit. And finally, liquid nitrogen. Should make them go down even more. Getting cooler and cooler and cooler. You see how low he's getting.
Okay. So now let's explain that behavior with the ideal gas law. That device was constructed so as to have constant volume. So the V here in the ideal gas law is constant. And we don't know what the gas actually was, right? But it doesn't matter if it's low density and described by the ideal gas law. It doesn't matter what it is. Okay, so what did he change in the demonstrations? He changed the temperature of the gas by putting that bulb, that sphere, in contact with different baths at different temperatures. And he discovered that whichever way the temperature change went, the pressure changed similarly. In other words, if the temperature goes up, the pressure goes up. He showed that on the pressure gauge. If the temperature goes down, the pressure goes down, if the volume is constant. So that's just another demonstration of the ideal gas law. All right, so now, here's the next thing I want to talk about. I want to look at a special situation because it's somewhat important. What's called an isothermal. Isothermal means constant temperature. And we'll look at an expansion, an isothermal expansion of an ideal gas. So we're going to imagine an experiment with our apparatus, like drawn on the left, with the cylinder and the piston on top and the hot pad thermal reservoir, the hot plate thermal reservoir at the bottom. And allowing the piston to move up or down means work can be done. And with the hot plate thermal reservoir at the bottom, energy transfer as heat, Q, can go in or out at our control. Okay? All right. And here's what we want to do. We want to do a specific experiment here. In this particular case, let's start at the point, we're going to have a PV diagram labeled I. So there's some initial volume at the point I and some initial absolute pressure, PI. And the temperature of the gas, let's imagine there's some kind of way to measure the temperature of the gas, is 310 Kelvin. That'd be a rather warm room. Okay, that's the starting point. And what we want to do is have the gas expand. The volume gets larger until we get to this final volume right here. And we want to do it, the expansion, such that the temperature of the gas does not change. We'll have a temperature gauge in there somehow, and we can watch it. And we'll do the experiment such that that temperature gauge shows no change. And I want to talk about what the PV diagram looks like and how you would do the experiment with the apparatus. To figure out how to do it, let's apply the ideal gas law or equation. PV equals little n RT. Let's use that. Let's just rearrange it for the pressure by itself. Okay? And let's note something. If we're going to do this experiment at constant temperature, then this combination, nRT, for this experiment, are all constant. So this formula for the pressure has the form of a constant over the volume. Okay? And that's what this curve right here in the middle of the PV diagram looks like. It's a plot of a function of the form y equals a constant over x. That's so you can see it. Okay? Y equals a constant over x. which, as you know, is a hyperbola. That just comes right out of this form over here from the ideal gas law. If I have an isothermal expansion, then the PV diagram has to be described by P equals a constant over V. And notice the P's upstairs and the V's downstairs. So as the V gets larger, the pressure has to get smaller. And of course, that's exactly what this curve right here in red shows. With an arrow on it. That's the PV diagram for this isothermal expansion. The volume gets bigger and the pressure gets smaller. That's what has to happen if it is to be isothermal constant temperature. Is that clear? I hope so. Now, let's think briefly with our apparatus. How would we actually do that experiment? You can imagine, you can conceive that we would put some kind of a temperature gauge in there that could measure the temperature of the gas so that you could have a readout of that. All right, so how do we do this isothermal expansion? Pause the video, think about it for a minute, see if you can come up in your head how to use this apparatus and everything we talked about it in chapter 18, and then come back. Okay, first, it's an expansion. The volume has to get bigger. That piston has to go up. So you got to make sure the locking pin is out, right? That's the first thing. Take out the locking pin if it was there. Now, I want the piston to go up, yes? And I want the pressure to go down. First question, how do I guarantee that the pressure goes down? Do you remember how to control the pressure with this apparatus? It's with these lead shots, yes? More lead shots in, pressure goes up. Take lead shots away, pressure goes down. I want the pressure to go down, so I have to take lead shots away, one at a time and slowly, because they're very small. So very small incremental change. That will make the pressure go down. But I also want the piston to go up. So I will, and while the temperature gauge reads constant, so I will have one other thing at my control. The thermal reservoir. Okay? And I will have to adjust it, adding heat as necessary so that the piston goes up and the temperature doesn't change, and you will have to add heat. Okay? So the directions are, the W goes up, in other words, positive work is done, it expands, and the energy direction exchange for the heat, Q, is in to the gas. Okay? This is an isothermal expansion. And each one of these curves that you see in the PV diagram, we're looking at that middle one, those are called isotherms. So the one we have there in the middle is the isotherm for the temperature 310 Kelvin. And for every possible temperature of the gas, there is a separate isotherm curve. And higher temperatures correspond to isotherm curves that are higher, and lower temperatures correspond to isotherm curves that are lower. So you see there's another isotherm curve drawn. It's still just a hyperbola with that formula, but now it corresponds to a higher temperature, 320 Kelvin. And there's a lower isotherm drawn, which is another hyperbola, but for a lower temperature, 300 Kelvin. So in an isothermal process, the system follows what's called an isotherm. Here's another question. How much work is done by the gas in an isothermal expansion? Well, graphically, the answer to that question is provided by how much area there is between the isotherm curve and the volume axis, right? That shaded area in green. That's the work done. The problem is I can't just use simple geometry to get that area, right? Because it's not a simple shape. I'm going to have to actually do an integral. But I still want to know how much work was done, so this is worth doing. So now we're going to calculate the work done by the gas. W by. So we're starting from this very basic beginning for a gas. I integrate the pressure, dV, from the initial volume to a final volume. Okay? And now I just substitute the ideal gas law. Which I rearranged up above as P equals nRT over V. So that's how I get the next line. See? nRT over V times dV. I have to do that integral. Now remember, when you have an integrand, if part of the integrand is a multiplicative constant, you get to bring it out front. So in our case, what are the things that are constant? Little n, r, and t. T in this case, right? It's isothermal. So you get to bring those out front, but only because they're constant. Then here's what's left for the integral. The integral from V initial to V final of dV over V. Right? That's the integral we have to do. So now I'm going to give you a little tip, something that's very helpful to know, and in fact something you need to know. We are now faced with a very famous integral, at least in physics, one that's very common. That's what I mean by famous. Very common, and we have to know it. Now, I'll write it in a generic form, where the variable of integration is x. An integral of the form dx over x. So what that's saying is that if you have a plot of y versus x, and you just got a hyperbola of that form, what's the area under that curve? Okay. What's the area under that curve? Well, your calc professors can explain to you how to get the answer. I'm just going to tell you what it is, but it's very important to know it. The integral of dx over x is the natural logarithm of x plus an arbitrary constant, if it's an indefinite integral. If you do it as a definite integral, the integral from x initial to x final of dx over x, then it's natural logarithm of x with the limits, x final, x initial to x final. So substituting in the limits, that's the log of x final minus the log of x initial. Then remember properties of logs. Log of a minus the log of b is the log of a over b. And that's the way the physicist would write it. The log of x final over x initial. That's the integral we need to know. Because that's the integral we have. I mean, the symbol is v. Our integral is dv over v, from v initial to v final. But who cares whether the symbol is called v or x? So now, here's our result then. Back to the work calculation. For the work done during an isothermal process. It also works for a contraction. W by is nRT, natural log of final volume divided by initial volume. Note the order, V final on top, V initial on bottom. You cannot switch that. And that's a handy little formula that we will use. We'll just go straight to it. If we need to calculate the work done by an ideal gas in an isothermal process. Please be careful. It's got to be an isothermal process. Otherwise, if it's not, stay away from this. Okay, so on Monday's class, we'll be practicing with these ideas. I'm just going to leave you with this video lecture with a class engagement exercise for Blackboard. Practicing with the ideal gas law. Goes like this. An ideal gas has an initial pressure of 3 pressure units. They don't really care what they are. They could be pascals. If you want to think Pascal, fine. And an initial volume of 4 volume units. If you want to think meters cubed, SI unit of volume, that's fine. All right. The table here gives the final pressure and the final volume of the gas in these same units in 5 different processes. There are the processes. They're labeled A, B, C, D, and E. And then you get the pressure value going across that way for each process, final pressure, and the final volume for each process. Okay, so in process A, in all cases, we start with an initial pressure of 3 and an initial volume of 4. 3, 4. In process A, just to make sure it's clear here, the final pressure is 12 and the final volume is 1. You see what I'm saying? Okay. So here are the 3 questions. A, which processes start and end on the same isotherm? That is, which processes of the 5 are isothermal? That's A. B, for each of those that are isothermal, state whether the gas expands or is compressed. C, for each one of those processes that is isothermal, state whether the gas does positive work or negative work. That's what you answer on Blackboard. Okay? All right, so that's the ideal gas law and our first example of applying it. We'll be talking about that in our class on Monday. That's all, though, for this video.